So we're switching gears. We did footing and foundation last week in the first class of this week. Now we're moving on to floor framing. And today I'm going to show you two PowerPoints. I'm going to show you like an overview of floor framing, and then I'm going to show you a PowerPoint on trusses. And then we have two assignments, and I'm assuming I'm going to give you enough time to get the two assignments done in class. Then we're going to learn how to use, in the beginning of next week, we're going to learn how to use structural sizing software from the company Weyerhaeuser. Those of you that are in the business, that's a big lumber supplier. And they've got a very good top quality software, and we're going to learn how to use that. And so lots of students actually tell me they like learning how to use Forte. It kind of gives you a sense of power once you learn how to use that. So make sure to come to Monday's class. And then we'll have a little assignment. We'll practice it in class, then we'll have an assignment I'm assuming you can get done. Then we have a floor framing plan, similar in concept to the footing and foundation plan that we'll be doing the second part of next class. And then we'll move right into wall framing. And just to give you a heads up on the roof framing one, I do have a guest speaker coming in to talk about trusses. One of the local truss manufacturers over in La Crescent. They're looking to hire one of our graduates to be a truss technician where they design the trusses on their software there. And so he wanted to come in, and I'm like, hey, I'm teaching about trusses. This would be a perfect class. So he's going to come in and talk to us. I'll let you know the date. I didn't hit my schedule here, but I think it's on my schedule on Blackboard. Okay, so that's that. That's where we're at with that. So I'm going to go ahead and show you my first PowerPoint. Now, what I used to do is do one PowerPoint and one assignment, and then one PowerPoint and the other assignment. I'm just going to show you both PowerPoints, I think, and then give you both assignments, and then then you can leave if you get done with everything earlier, or take a more of a break. Okay, so let's get started here. Slideshow. Okay, so I'm gonna, since we're learning about doing houses and light gauge framing, I do light wood framing. I do focus more on wood, but I wanted to let you know that a lot of the concepts that we learn about in wood framing are just the same for light gauge metal framing. So on my picture on the left here, just like you can have wood studs and wood joists and wood decking, you can have steel studs, steel joists, and steel decking. It's the same concept. So just to kind of go over the pictures here, this is a picture of steel trusses. Now we're going to talk about wood floor trusses in my second PowerPoint. And this is a picture of a house that was framed in. And, we talked about the footing and foundation plan. This is showing the rim board. It's showing the sill plate with the anchor bolts. These are wood eye joists or TJI joists. And you can see, since they're made in a factory, they can make them span much longer than you can get a straight 2x10 or 2x12. This is an engineered lumber beam. And I don't know if these are the actual columns or the temporary columns. I'm not quite sure. I'm trying to find where the footing is. I think I'm seeing the edge of the footing in here, but it's kind of under construction. But this is what would be called the dropped beam, and we'll talk about that a little bit later. So when I say it's a dropped beam, that's because the beam is dropped below the level of the floor joist. Okay. So let's talk a little bit about if we have a floor member and it's spanning. We talked about tension and compression in the past, but now I want to talk about bending. Now let me see if my visual aid is still here. So if I've got a member that's spanning horizontally, it's not in only tension and only compression. It's in both of them. And I can't bend it with my hands this way. I'm not strong enough, but I can bend it this way. And you can see that if I exaggerated this upper diagram here, if I exaggerated a beam that was under load and being bent, the top gets smaller because you can kind of see that top is a smaller dimension than the bottom is. The bottom stretches out and the top compresses. So the top of the beam's in compression and the bottom of the beam is in tension. So that's what's happening in bending. It's two forces. And this little diagram down here, the compression force, the bigger it is, the bigger the red line is. So the most compression is actually at the absolute top surface of the beam. The most tension is in the absolute bottom surface of the beam. And so that force starts out really high at the top. It decreases and decreases till it gets to the neutral axis or the middle of the beam, and then it's at zero. And then it starts to get tension below that neutral axis until it gets to the bottom where the tension is the highest. So how this works in the real world, I don't know if you guys that did construction, but if you're ever going to drill a hole in a floor joist, you typically drill it in the neutral axis. And the reason you were taught that was because that force goes to zero in the neutral axis and it's okay to drill holes in it for the most part. Now, sometimes if the holes are located closer to one end or the other, it's not okay to draw holes or you're limited in the size of holes. And we'll get into that in one of our assignments. But the problem that happens is that if you drill a hole in the top and the bottom of a beam, imagine your intention in the bottom of the beam and you drilled a notch, like say you notched for a plumbing pipe to run in the bottom part of the beam there. That part of the beam from on either side of that notch is worthless, right? Because it can't pull tension through a hole where that notch was. Okay. So what that's doing is it's making the depth of the beam shorter by putting a hole in the top or the bottom. You're actually decreasing the structural strength of the beam because depth is critical. When you do the bending calculations, the depth is cubed. Okay, so as far as the strength of the beam, it goes up by the cube of depth. So if my depth goes up 2 times, it's like from 4 to 8. What is 4 cubed? 4, 16, 64. What is 8 cubed? 64 times 8 is 400, and it's like 500 and something. So the strength goes up geometrically cubed as the depth increases. And that's why Wimpy Pete can bend this beam just with my fingers this way, and I can't bend it this way, right? Because it's so much stronger in the vertical location. Same way that they don't make diving boards that look like this, right? They were too strong. They wouldn't bend at all if they were straight up and down. They have to be laid flat because then there's no depth there and there's no bending strength there. Okay, so long talk about why we drill holes in the middle of the beam. So now remember this little diagram here? And this explains why all these floor joists and floor members look the way they do. Because we just found out that depth is critical and that there's the most stress at the top and at the bottom. There's the most compression at the top and there's the most tension at the bottom. So do you ever wonder why they call them I-beams? The technical term is wide flanges for the most part. Do you ever wonder why wide flanges ended up being that way? Because they're putting all the material at the absolute top and bottom because that's where all the stresses are. Same thing with wood eye joists. They're putting all the material at the top and the bottom because that's where most of the stresses are. And the purpose of, so those are called flanges. And the part that goes up and down is called the web. And the purpose of the web is just to keep those flanges separated out. So the same concept applies to open web bar joists or floor trusses. Now these are metal open web bar joists. So if you go to the 4th floor and look at those, that's what those are. And again, look at this. We've got all this structural members happening at the absolute top and bottom, and the diagonal webs are just there to stabilize that and keep those things apart at the top and the bottom. Same thing with wood floor trusses, which we'll talk about in our separate PowerPoint. You put a big honking piece of wood at the top and the bottom, and then you just have diagonal pieces to separate them. Okay, now we're going to talk about another force that impacts beams. And so we talked about tension and compression. Compression is pushing, tension is pulling. We talked about bending, which is a combination of tension and compression. Now we're going to talk about shear. So if you've ever heard of, do I have a scissors up here? Yeah, have you ever heard of scissors called shears? So think about it. You on a shears, you've got one blade going past the other, and that's how you cut things. Well, you have that same force happening in buildings. So when, if you can imagine, the wind is blowing at the top of this wall here, and it's anchored down at the base of the building. So those forces are in opposition to each other. So if I'm blowing wind at the side of the building and it's the bottom of the building is anchored to the foundation, it wants to move that top of the wall over in the direction of the wind. So have any of you bought like a cheap bookcase at Menards or Home Depot or something, and it's basically like particle board, and they're kind of notched together with each other, and then you push on them and the whole thing like tips over like a house of cards. But then they give you this tiny little sheet of cardboard or particle board or something, and you nail that into the back. That acts as a shear panel, and it keeps it from racking and tipping over. So the way that OSB or sheeting on a house works is that's a shear panel, because when the wind's blowing on your house, there's nothing to keep those studs from wanting to tip over like that unless you nail them into the OSB, and that's acting in shear against those lateral forces. So on a commercial building like this where we don't use wood, you probably notice like when you go into our stairwells, those walls are all concrete block. Those are shear walls. So those walls being block, they provide that shear strength that keeps this building from like wanting to tip over if there was a strong enough wind against it. So the floors transfer the load to those shear walls, and those shear walls try to stabilize the building laterally. Now let's talk about beam shear on the next slide. So imagine I've got a very heavily loaded short beam. And it's being held up. I'm going to use my scale here as my column on the end. If there's enough load on that beam, it could theoretically like shear the beam, like the column part would stay there, but the rest of the beam would kind of push down because there was so much load on it. And this typically happens in short, heavily loaded beams. The other beams fail in bending. The long, lightly loaded beams, they fail in bending or in deflection. But if I have a very short, heavily loaded beam, it might actually shear this. So like if I was strong enough and I put enough load on here, I could actually rip this wood if this was an immovable object and I put enough force onto it, okay? So the way to think about that is, imagine a beam is made up of a bunch of magnets together. Now, beams aren't made up of magnets, but they do have a force holding them together, so that if I put a force down, they don't slide down like a bunch of magnets in relationship to each other. So there's an internal vertical force that's required in a beam. So when you size them by hand, you check bending, you check deflection, and then you check shear. But shear was typically like this little diagram shows at the bottom of my page here. That's only going to happen on a very short, very heavily loaded member. So now let's talk about the last one I talked about. So I talked about bending, I talked about shear. Now I'm going to talk about deflection. So deflection's the amount the member sags when it's fully loaded. So if I've got my floor joist and I'm putting load on it, it's going to sag down. Now you might not be able to see it. Sometimes you can actually see it. Like if you go out there with a laser, sometimes you can see that that floor is slightly sagged, down. So deflection's the amount of weight, the distance that structural member sags. So as you all know, if you walked across the tightrope, you put a load on it, it sags down. That's deflection. Wood, steel, any structural member that you load, it is going to deflect. Now, do we ever design a house that can't deflect even like a tiny fraction? No, it's always going to deflect a little bit. The thing is, we have to be an allowable limit on deflection so it doesn't cause troubles. Now, how can it cause the troubles? You can crack your finishes if it deflects too much. And also, have you ever walked on a floor where it just feels bouncy and you can hear the dishes rattling in the china cupboard? That's because it's deflecting too much. It's not stiff enough. So typically on a drywall or a plaster ceiling in a house, plaster is more prone to cracking than drywall is, but they try to limit the deflection to L/360. So what you do is you take the length in inches of the beam, or the floor joist. So if this is 12 feet long, that's 144 inches. If we want to limit it to L/360, we take the length, which is L, 144 inches, we divide it by 360. And that means that the maximum deflection would be 0.4 inches. So we're obviously exaggerating it, but if it was fully loaded in the center of that beam, if we had a laser beam, it would never sag more than 0.4 inches. Now, sometimes on the charts, you'll see L/240. Maybe if you don't have any finishes and you have carpeting on the floor, that would be acceptable. I think L/360 is really standard. I have seen L/480. So like say you want a stiffer floor with less deflection, you would do L/480. Believe it or not, some stone tiles that they're very prone to cracking, they want a floor deflection limited to L/720. So that would be a very little amount of deflection. So as we're going to find out once we get to Forte, you can have a structurally sound floor that's never going to collapse, but people don't like the way it feels when they walk on it. It doesn't feel solid, okay? And so the people that make the wood eye joists, the Weyerhaeuser company, they've actually done tests and they give you a rating on how stiff the floor feels. And we'll get into that when we get to the Forte software. Most of the things I ran into in the working world were deflection related. People didn't like that their floor felt bouncy. People didn't like the fact that you could hear the dishes jiggling in the china cabinet when you walked around. And you've all probably experienced that. Believe it or not, Coleman, I don't know if it's still like that, but Coleman, when I walked through like one of the big labs in there, I could literally feel, I'm not a big heavy person, right? I could feel the floor bounce when I walked through that room in Coleman, which is very rare in a commercial building. And when you walk on this floor, do you feel it bounce? No, it's solid as a rock. Okay. But on wood frame especially, they're prone to deflecting and not feeling as solid as people want. Okay, now let's talk about two load types on a structural member or on a beam. So point loads act as one point. So if I have a column coming down from the second floor and it's sitting on my first floor beam, that's called a point load or a concentrated load, because you're taking a lot of load and you're putting it at one point or you're concentrating it. Now, if you've got like a load that's spread out, so like for example, let's look at this beam here. We've got all these floor joists, 16 on center, 24 inches on center, whatever it is. We don't treat every time that floor joist hits as an individual point load. We treat them as a uniform load. So we take that load and it's spread out over the beam. And so if you draw a diagram, the point load's like an arrow, because that's like a huge load, like a column where it's like 8,000 pounds coming in on a 4-inch square. The uniform load is all the floor joists coming in every so often puts a uniform load on the beam. It's also called a distributive load. And the same tributary area, remember when we did the footing design assignment, we did the tributary area and we figured out how much load was coming into the footing? That same calculation tells me how much uniform load is coming onto my floor beam here. So let's use an example here. So this is a 24-foot wide house and the total load is 55 pounds per square feet. So this is 12 feet on this side. This is 12 feet on this side. So that means half of that 12 feet, 6 feet goes to the foundation wall on both sides. And half of that 12 feet, 6 feet goes to that beam. So when I say the beam takes 12-foot tributary area, do everybody understand how we got that? That's our old half and half rule. So 12 feet overall is going onto this beam. So if my loading is 55 pounds per square foot, that would be I take 12 times 55. My uniform load on this beam would be 660 pounds per foot. Okay, so every foot of that beam, we assume that it's getting 660 pounds dropped on it from the floor joist. Does that all make sense? Hopefully, okay. Now I've been using a lot of terms here. Let's get my terms straight. So floors are made of flat horizontal spanning members. They have different names depending on what they support. Joists are the smallest structural members. They are regularly spaced and usually hold up the floor deck that people walk on. So when I'm talking about floor joists, that's the horizontal member that our plywood goes over that. That's what the bulk of the floor is. Now, sometimes you hear people call beams and girders the same thing, but they're not. Technically, a floor beam holds up a joist. So a joist, a member that holds up multiple floor joists is called a beam. A bigger beam that holds up multiple beams is called a girder. Okay, so in this case here, we've got floor joists spanning to beams, and then we've got beams that are spanning between girders. So the girders are the biggest one that holds up beams. The floor joists get held up by beams. So the girder, so you can't, technically you shouldn't be calling beams and girders interchangeable names, but I have been out on job sites and people talk about girders, but they're really just holding up joists, so they should just be beams. So now we've got our joist. So here's a wood eye joist up above, and it's being supported by an engineered lumber beam. That looks like a paralam to me. It's an engineered lumber piece. These are wood, looks like 2x10s or 2x12 floor joists, and they're being held up by another wood 2x10 or 12 built up beam, right? So there's like 4 layers of beams that are, joists that are 2x12s that are nailed together. So we have 2 different conditions here though. One of them, the joists come into the side of the beam. That's called a flush beam. Where the joist sits on top of the beam, that's called the dropped beam. And so here I found a picture that has both conditions in the same deck. So these people are building a deck. And here you can see we have the floor joists or the deck joists going this way, but then they're being framed into the side of a beam with like a joist hanger. So that on this lower part of the deck, we have a flush beam. On the upper part of the deck, you can see right where my mouse is, they're sitting on a beam that's dropped down, and then there's a beam drop down here that they're sitting on. So there's a drop beam there and there's a flush beam here. Why do you think they didn't put a dropped beam on this lower part of the deck? Any guesses? It was gonna be into the dirt, right? And so like if there's a raccoon building a nest down there, you're not gonna be able to see it. If your beam's gonna be sitting in the dirt, you can't make sure that there's nothing going on in there. So they did a dropped beam on one side and a flush beam on the other. But we're gonna talk a little bit down the road how this impacts your HVAC if you do this in your house. So let's imagine this is the basement of the house. Maybe I'll talk about it now. So imagine you're in the basement of the house and you've got a big trunk line that's running from your furnace, and you want to get your branches out to the outside walls of the house. So when you do a dropped beam, what happens is they run their trunk line alongside the dropped beam, and then they can bring their branches out in between the floor joists and run it over the top of the beam to get to that wall. Very, very common. The reason that they typically try to avoid doing dropped flush beams is that if you've got your HVAC line down here, you have to go under and then come back up. And so it's more work, and it actually takes up more space for the duct work because you got to come out and then up and then over versus coming out over the top of the duct and running over that beam. I've got some pictures to show you how that works. So now we're going to do some more terminology. So these are joists. Around the end, there's a rim joist. I've also heard it called a band joist. What's the other names have you heard it called? Rim or band is rim. So around here, I guess rim is the key. So you can see this is engineered lumber made out of OSB. These are the wood eye joists running from wall to wall. So the spacing is the distance. So if I say I've got 11 and 7/8 inch floor members at 16 on center, that 16 inches on center is the spacing. So that's either 16 inches on center or 24 inches on center or 19.2 on center. You'll notice all three of these, they work with 48-inch wide sheets of plywood. Now I've never used 19.2. In the real world, do you use 19.2 at all? You did. Okay. So how does that work? You get three, how does that work with the 4x8 sheets of plywood? I know the 16 and the 24, that makes sense to me, but the 19.2, I can't figure that out. It's been a while. Okay. So anyway, 16 and 24 are the two that I typically use. We don't typically go less than 16 because again, if they're trying to put ductwork up in between there, if it gets too tight to work in, if you get your floor joist space too close together, the people that are running the HVAC and the plumbing and everything, they prefer to have 24 or at least 16. So we typically won't go to 12 inches on center, even though technically we could make the joist 12 inches on center. So that's the spacing. And then the span is the distance that your joists are spanning, either between a bearing wall at the foundation, a bearing wall in the house, a beam, and a column on the inside. Okay, so we're working our way up from the foundation. So how does all this floor framing get attached to our foundation? So we talked a little about anchor bolts last time. It's literally the only thing holding the upper part of your house onto the foundation. So back in the day, I don't know if they still use this a lot, but they made this like gushy foam that makes up any difference between the sill plate and the top of the foundation wall, just so that there's not air gaps in there for like the wind to blow through. Do they still use that or they just use sealant? They still use that?
Still use it.
Okay, so yeah, they still use sill seal. I have seen some jobs where they just put a heck of a lot of sealant on below the plate when they put it in. So the sill plate sits on the foundation wall. It's typically pressure treated. And then the anchor bolts are specified by code because that's the only thing that's holding that house on. That's the only connection between all the wood structure above and the foundation. Okay, so your assignment next week is going to be a floor framing plan. And these are just some things to remember for that assignment. I don't expect you to memorize it. You can come back and look at this. So floor joists are typically oriented to span the shortest dimension between supports. So for example, on this house, which is a long skinny house, if my joists can span this direction, I typically would span them the short direction instead of the long direction. The supports are either going to be beams and columns, load-bearing stud walls, or foundation walls. So anytime you've got an opening, you need to double up your member on each side, because when you think about it, all these joists, they can't go to their bearing over on the foundation wall because there's like a stair opening here. So we would have a doubled up member here, or maybe a tripled up depending on the span. And then that's putting a point load on this other double or tripled up member here. So all this load eventually has to get down. Half of it goes to the wall, half of it goes here, half of it goes up, half of it goes down. But then most of it comes in on this member onto that wall. So that's why you have to strengthen the framing at openings. And then you also have to keep in mind how your HVAC ducts will run. So if we want to get typically we want our heat ducts to be at the outside wall, we're going to run our trunk line down the middle or probably the middle of this house. And we're going to run our branches off to each side to serve the heat coming at the outside wall. Now, why do we want the heat at the outside wall? Why don't we just put a bunch of floor registers in the middle of the house? Why are we so concerned with getting those heat things out to the outside wall? Any ideas on that? The same reason, why do we have a baseboard heat along that window there? Because what's happening is all the cold air is coming off of those windows, And what does cold air rise or fall? It falls. Cold air falls. So the cold air is falling off those windows. And if we didn't have that heat there to counteract that, your feet would be getting cold. Like Shane and Amber's feet would be getting cold because that cold air would come, sit at the ground, and start to move its way in. So that's why typically on a house, we don't blow our air in the middle of the room because it's that hot air is going to rise up to the ceiling and it's going to hit the windows, cool off, and then there's going to be this constant loop of cold air running around the floor. So if you've ever been in a house where your feet are cold, that's probably what's going on. They didn't get you enough heat out at the outside wall. This is a Cadillac system here because what's happening is it hot today? Oh yeah, it is. So this is counteracting that cold that's dropping off of this window. It's mixing up with that hot air rising up of there, and that's why your feet aren't getting cold when you're sitting against the wall here. Okay, so that's a little bit of HVAC basics. That why structural and HVAC kind of interact because our HVAC has to run through our structure in a lot of cases. So I talked about how framing must be strengthened at openings and overhangs. So the one at the top where the joists are framing into it is called a header, and that's typically doubled or tripled up depending on the size and the loads. And then the one that's on each side is called a trimmer. So here you can see double trimmer joist, double header joist. So we don't typically double up these wood eye joists because they're not made to take point loads at certain points. We typically use LVLs, like double LVL. So here you can see there's a double LVL. There's another double one here. They're joist hangered. They're joist hangered because they can take that point load. And then our standard floor joists are wood I-beams. So this was actually at a student designed house, the last one that was constructed over in Rockland. I took a picture of how they framed the stair opening. Now, how many of you ever seen these little X's when you went into your basement and you looked up at the floor? I've seen nodded heads. Okay, so that's called bridging. And if you saw one where it was just a piece of wood between them, that would be called blocking. So blockings here, these are diagonal bridging. Sometimes they make them out of steel where they just have a little prong at the end and you just hit them with a hammer and drive them in. Sometimes you actually have to nail them in and they're little pieces of wood, 1x3 lumber with beveled ends. So those are required with sawn lumber. They're not required with engineered wood. And the reason is that the sawed lumber is more tending, the one that comes out of a tree, it's tending to warp and twist and everything. And it's trying to keep those perfectly vertical with each other so that they can carry more load if they're vertical than if they're laying on their side diagonally or if they're warped and twisted out of the way. So they want them to distribute the load. If one joist is overloaded, these help to distribute the load and keep them perfectly vertical. And the code actually tells you when we get to the next semester, there's a code question that tells you you need to provide diagonal bridging, bridging, on floor joists of a certain size with a certain span. The code will tell you you have to do that. So now let's talk about HVAC one more time here. I kind of gave you a quick preview of what I'm going to be talking about. If you do a dropped beam, you're going to run your duct line most of the time right alongside. And the reason they do that right alongside is that if you're doing a finished off basement, you don't want to see the duct work and you don't want to see the beams. They typically build what's kind of soffit. They soffit out around that. So you can see they build like a bulkhead on both sides and then they span across there. And so it looks nice and integrated when you have your finished basement. And by putting the trunk line and maybe the water piping or whatever, maybe some plumbing lines, we can get all that into one dropped bulkhead or soffit. Here's that same house in Rockland. So that there's a dropped beam to the left of it. And you've got a supply beam, so a supply trunk line, and a supply duct that runs up in between the floor joists. And so that's going to the outside wall so I can get my heat coming in on the outside wall. These little doohickeys here are how they adjust the airflow. They're balancing dampers. So where I'm highlighting there, if I'm getting too much heat in one room, I can go into the basement and adjust them so that I can balance out the amount of air that's in the various rooms. I'm going to show you a picture, another picture of the overall in Rockland. So this is the stair. Here's our LVL beams. Here's our FHA columns. So FHA stands for Federal Home Administration. They're rated columns for a certain load. They'll have a label right on them that'll tell you how many thousand pounds they will take. They're adjustable. They've got a little screw-in piece at the underside, and these are installed the right way, where the screw-in is supposed to go down. It's not supposed to go up. And in some cases, it goes down and you don't even see the screws after the slab's poured because the slab covers up where the screws are. So we designed this house with a steel W8x10 beam with a 2x wood plate on top. But Habitat actually changed that to LVL, which is laminated veneer engineered lumber, because it's easier for volunteers to work with. Because like a steel beam, you have to deal with the steel supplier. They do a shop drawing of the exact length where you want the holes drilled in it. They cut it. It's a lot more dinking around. Whereas an LVL, you go to Menards and you buy some LVLs and you come to the right length and you nail them together and you're good to go. So that's that. So now let's talk about if we do a framing plan, what's our philosophy? Do we draw every stick or do we let the builder lay out the typical joist? So computers have made drawing every stick easier, but you still need to make sure it's clear and easy to read. So I showed you this house already. This is the one up on French Island. That's my floor framing plan and the lower roof framing plan for that house. So here's the floor framing plan. And then this is a low roof, this is a low roof, and this is a low roof. Since this was done in CAD, I drew every stick. And I also did a schedule to avoid a lot of annotation on the plans. So if I look at this where it says floor joist 2 or FJ2, if I look up here, it's a FJ2 is a TGI Pro 250 series 16-inch deep I joist at 16 on center. If I look there where it says H2, that's my header schedule. So that's 3 1 3/4 by 9 1/4 micro lamps. Those are LVLs or laminated veneer lumber. So by doing a schedule, now later on in the book they talk about schedules, but by doing a schedule, instead of having to write exactly what size, all that writing on every one of these headers, I just put a H2 up there and they can see it once. It keeps my plans a lot clearer and easier to read. And so notice here, structural schedule on the notes, I've got 1s and 2s. 1s are flush beams and 2s are dropped beam. So if I look at this 2FB4, which is 3 1 3/4 by 14-inch LVL micro lamps with 3/4 inch flitch plate, it says 2. That's a dropped beam there. So I'm telling them which ones are dropped down below the floor joist and which ones are flush with the floor joist. I already talked about this one's. This is the house I drew for my parents by hand. I'm drawing all these lines with a pencil. I am not going to draw every floor joist because it's stupid in this case because I'm trying to show a lot of other stuff because it's a combination footing and foundation and a basement plan and a framing plan. So I just tell them that I'm going to use 11 7/8 inch TGI's 15 series at 16 inches on center, and they can figure out how they're going to lay it out. They don't need me to draw every stick. So there's some cases where it makes sense to draw every stick, and then there's other ones where it really doesn't. Your boss will probably tell you which way your company likes to do it if you end up doing structural drafting. So I talked about this before in the other class. I do want to give you guys a little quiz. So there's my floor joists, they're running up and down. There's my beams. I use parallel strand lumber, 5 1/4 by 11 7/8, and they're all 5 1/4 by 11 7/8. Some of them are dropped, and one of them is flush. Why did I make that one beam flushed and the rest of them dropped? Yeah, because my dad's tall and I'm tall, and to maintain code required headroom, I couldn't do a drop beam because my dad and I would both be bonking our heads on it. And even if the code So the code minimum, I think for his headroom at a stair is like 6'6" or 6'8". I could be wrong at that. All I'm gonna tell you, as a 6'4" guy that has run down a lot of stairs, bouncing up and down, I've hit my head on beams running downstairs, and it isn't fun. Okay, so next thing you know, you wake up and you're laying on your back on the stairs because you bumped your head on it. So anywho, the other thing is just a reminder, I'm showing my load in kips, which is 1,000 pounds, so 9.3 kips or 10.2 kips, this would be 10,200 pounds. And so then I'm saying that that's one of those adjustable steel columns rated for the stated load. I've got a Simpson column cap field welded on top. Then I'm sizing my footings for the worst case. So if my worst case was 10.2 kips, I'm running the loads with my 2000 PSF soil bearing, and I'm coming up with my size of my footing. So these footings are 30 by 30. Now in reality, I might be and have been able to go by with like a 24 by 24 or a 28 by 28. But it's not worth my time to size all those to save them 5 cents worth of concrete and make them form up a different size of footing for everyone. So you size the worst case and they do them all the worst case, at least in this one. And I have 4 number 4s each way. So I'm doing a number 4 rebar, which is a 1/2 inch diameter. I'm doing 4 of them spaced out one direction, and I'm doing 4 of them spaced out the other direction. And that's a good thing to do here because I'm dropping 10,000 pounds on it in a tiny little area. I want to spread that load out. I don't want that column to have the ability to punch through my footing. So that rebar keeps that concrete together and keeps it from going into, if there's a tension involved or a shear involved, it helps that. Okay. So I've been talking for 50 minutes. We can either do a break and then do my second PowerPoint, or I can try to get my second PowerPoint done and then give you a break. Second PowerPoint is 8 slides on trusses. What would you prefer to do? How many want to take a break now? 1, 2. How many want to keep going and take a break after the PowerPoint? Nobody. Okay, so we're going to take a break now. So let's take like a 7-minute break till 25 after.
You would hate my house. I'm 5'6" and I can hit my head
Oh,
on the way down my stairs.
yeah.
But it's an old house. They
Yeah,
got
they
it.
didn't have codes back in the day.
Yeah.
In Jen's class, we did get graded on how long we would line up.
We did. You looked at the red
So
lines
she
and then
would red line after and catch things that you missed, get points off.
if you didn't do a good enough job red marking. Wow, that's pretty hardcore. I should try that. Was it stressful or did you?
It was so stressful. We would have 2 days, like not really 2, like the end of class one day before the start of class the next day, to take the documents home and redline. Like we were redlining for hours.
And you don't have enough experience to really, that's one of those things that as you get more experience, it's easier and easier to red mark if you've seen so many different drawings. So I can see that would have been pretty challenging.
It was so
Did you have to
stressful.
do it like for your capstone?
Yeah.
Oh, wow.
Well, for the construction, we had a construction document class at the same time as we had codes class.
We did, okay.
That was the hardest. She finally separated them
Well,
because
because
people were failing.
it was too much work.
Yeah.
So that's, as a teacher, that's one of the things you have to constantly adjust is like, you can set up a class based on what you think is a reasonable amount of work, but until you teach it to 3 different cohorts, you really don't know. Because like some cohorts, they get certain things better than others do. And so they can take more work than you have allotted to them, but then other cohorts, you're overwhelming them. So you got to kind of do 3 and kind of get a sense. And then the other thing is you can't give people too much without time to process it. And if you stress people out too much, they just like lose hope, right? Because we can't teach you everything you need to know in 16 months. It's just not doable. So we have to kind of give you a reasonable amount so that you're comfortable going into your first job, but you're going to learn a lot of it on the job.
Yeah, what was it, 2 days, we would get a new stack of Pete's notes, basically, that we would have, we didn't have like a book to follow, we just had the notes and create the construction document off of that.
Oh, really? That sounds pretty challenging. Was that in your second term or your third term?
Yeah.
It was in your second term. Okay, I'll give you a minute here and then we'll get started again. Okay, let's get to our second PowerPoint here, and then I'll talk about your 2 assignments and then give you work time on them. So I could have had the truss person come in and talk about floor trusses, but since the wood roof trusses are very, very common, I'm saying what, 90+% of the houses around here have wood trusses. So I'm gonna have them talk as we're talking about wood truss roof framing. But anyway, you can do your floor framing out of trusses too. So let's go ahead and watch your slideshow. I think again, if you can deal with the lead time and your spans are realistic. So I helped one of my friends and his wife, they built their house themselves. And he decided I went to school with him, so he's an architect too. It was a simple ranch house, but he decided to do floor trusses because he didn't want any interior columns or bearing walls in his basement because he was a woodworker and he wanted to have a nice big wood shop without having to work around columns and stuff in his shop. So in that case, a crane and a truck came out and they set all the trusses and they were able to clear span. So like when his kids moved out, and if he wanted to, he could have torn out all the walls in his basement and made it one big open shop with no columns in it. Now, he ended up not doing that, but that's what it was designed for. So let's talk a little about trusses. So we talked about how the stresses are all concentrated on the top and the bottom chord. So the diagonal webs are there to keep those top and bottom chords apart. And the reason we make them out of triangles is a triangle is a non-deformable shape. So if you ever look at like a radio tower or a TV antenna, they're always made up of triangles. Because if you just have 90-degree angles, you can take one and the other and it would rack, right? It would move in relation to another, but triangles, they're not deformable. So that's why we always have triangular spaces. Now you'll notice in the center of trusses, a lot of times they leave a rectangular or a square space, and that's in theory for running a duct. So that would be like where your trunk line could run in theory. So that's called the duct chase. And they also have open spaces where we can run like plumbing pipes or smaller HVAC ducts or electrical wires. So like on a normal framing where you've got a solid member and you've got a plumbing pipe, you've got to drill a hole if it has to run through something. Or if you got an electric wire that's got to go between one joist spacing to the other, you got to drill a hole. Trusses are great. You just go up there and run them wherever you want. So you get a lot. If you're subs that do that work or you're doing it yourself, you get a lot less labor involved in plumbing and HVAC and electrical, maybe not HVAC, but electrical, by not having to drill through all those joists. Okay, so let's talk about, there's 3 different ways these trusses can bear or be held up. One is that if it's being off the bottom chord, if that's what it's bearing on, that's called bottom chord bearing, logically enough. So the bottom chord is the one that's sitting on the bearing. In this case, it's on a joist hanger, but it's still bottom chord bearing because the bottom chord is where that load is going into it. Now, this is probably the most common. Now, you'll notice this here. We're going to talk about that later, but keep that piece of wood in mind. So the downside to this is that, let's imagine we're doing a house and we want wheelchair accessibility. By code, our grade has to be 6 to 8 inches below the first piece of wood on the house. We can't run our dirt up along the trusses, right? Because it would rot everything out. It would rot all the wood out. So that code, by grade, that code has to be down 6 to 8 inches below the lowest piece of wood. Now I'm trying to get accessible ramp up there, and my ramp maximum slope is 1 inch for every foot. So now let's imagine this is 8 inches and this is a 16-inch truss. I have 24 inches I've got to get from the ground up. I have a 24-foot ramp I got to figure out how to fit in my front yard. So the downside is that, hey, this is a little bit of a problem for accessibility because these trusses end up getting pretty deep because they're typically trying to clear span something. And now I've got to get all the way down the whole length of the truss plus 8 inches down to the grade. So I end up with a lot of either steps or a long ramp to get up to the house. Okay. So the way that they avoid that is they do what's called top chord bearing. So they typically double up the 2x at the top. So you can see there's a doubled up 2x. And so I'm only coming up 3 inches. So now if my grade is 8 inches below the top of the foundation wall plus 3, that's 11 inches. So I've gone from a 24-foot ramp to 11-foot ramp, which is a lot more doable. And it also allows the beams to be recessed into the floor. If for some reason I didn't have to worry about where my HVAC trunk was, you can see in this case, there's a steel beam running along with top chord bearing trusses, and it allows that beam to be set up so it's not hanging down below the trusses. Now, what's the downside of top chord bearing? I lose space in my basement for headroom. I've got to make my basement wall taller to get the same amount of headroom. So there's always a trade-off. There's not ever one right solution. And then there's one, it's not a top chord, it's not a bottom chord, it's called a mid chord. And the reason you would do a mid chord bearing, and you can see, you can make this mid chord bearing whatever you want. They just take a couple studs, turn them on the end. If you tell them you want them to be 4 1/8 inch, they'll make them 4 1/8 inch. The reason you do that is like if you've got an existing foundation and you're building on and you've got a certain framing depth and you want to keep the top of your floor joist to match the existing framing, you can make that height whatever you need to be to match up with the existing framing if you're building onto an addition. So here in this case, you can see this is a 2x4 laid flat, and then these are 2x4s, and these are called gang nail plates. So what they do is I'll show you more about how they make trusses, but just to give you a little peek onto this. These gang nail plates have very, very sharp fingers, and you lay these things all out on a table. In some cases, they actually have lasers coming down on the ceiling that show you exactly where they lay these things out on the table. And then they put these plates on top, and then they just hit it once with a hammer to hold it in place. And then there's this huge roller that rolls over the trusses and presses them all in. And it makes those joints lock together. So there's no nails involved. There's just these plates, and you can kind of see these sharp fingers. I used to have one of these that I passed around, but those fingers are so sharp, it was actually, people were potentially going to cut themselves and bleed all over their desk. If you've ever tried to tear one of these out, you can't hardly do it. You almost have to destroy the wood to get them out. They don't just pop out. So anyway, we're going to learn more about trusses when we have our guest speaker and we talk about roofs. Okay, so that board I was pointing out, that's called the ribbon board. So this 2x4 ribbon board, it provides support for the edge of my OSB subfloor, right? Because if this is 24 inches on center, this gives me a place to support the edge of that panel. It helps the installers line up the trusses and keep them at the right spacing while they're installing it. But it's not intended to hold up the weight of a deck. So you're not supposed to take a lag bolt and lag bolt your big deck into there, because that's only meant for the lining up the trusses and supporting the edge of the subfloor. You're going to need a bigger honking piece of wood bolted on or built into the truss if they wanted to, that would provide space connection for a deck. So we talked about our ribbons. Now let's talk about our strong backs. So strong backs help distribute the load. So like if I'm putting a lot of load on one of these joists, or these trusses, I should say, the strong back, as it sags down, that strong back will spread some of the load to the adjacent trusses. And it kind of stiffens the floor system and it reduces the amount of bounce that floor system might have. So the truss drawings will tell you where you're supposed to put the strong backs. They're typically every 10 to 11 feet. So you go over 10 feet, you put a strong back. You go over another 10 feet. If you've got a really long truss, you put another strong back. So you can see the ribbons on the outside and the strong backs are on the inside, but the strong backs are meant to tie the floor together. Okay, so this is the best case scenario. If you get your trusses all laid out properly and your HVAC people are online with it, in theory, they can get their ducts. So this is called a trunk line, just like a tree, and this is called a branch, just like a tree. Typically, you can get your trunks and branches in the trusses. Now, the problem is it's harder to install your duct in this trunk, especially if you're like trying to insulate it and doing the connections. So, you know, if you've got it all set up and you can push it in from the end, and in my experience, unless you've got the HVAC people online from day one when you're designing the house and they agree and they say, hey, we'll figure out, based on this layout you're showing us with the floor trusses, we can get our HVAC ducts up in the trusses. But if you just leave it up to them, it's a lot easier for them to run it underneath. So I've seen a lot of jobs where we put floor trusses in and we were hoping that the HVAC, when they came in and did their bid, would be able to run their ducts up into the trusses. And they're like, yeah, we can do that, but it's an extra X $1,000 because it's so much easier for us to just make them, screw them to the underside and be done with it. Now, did you guys ever run into trying to get your HVAC people to put all your ducts inside a floor truss? You did? Did they do it for you?
Yeah.
But were they online from day one?
I want to say, yeah,
Yeah.
we had some siding on them and tear off, and we had to cut plywood open.
So you had to cut a hole at the end so they could thread the duct in from the end. Yeah. So in theory, though, this is a great way of doing it if you can get it all to work properly. Okay, so that's the end of my PowerPoints. Now let's get you into some real assignments here. So I've got 2 assignments for today. They're both up on Blackboard. The first one is about TGI projects, TGI products. So we're going to talk about that. So let me find the assignment. Oh, I'm going to find. So this document is posted up to Blackboard and PDF. So this is Weyerhaeuser. This is a big lumber company that's nationwide, and they make a lot of these engineered wood product materials. And they have very good architect support materials, and they also make the software. So I took one of their copies, and I'm going to ask you to use this copy to answer the assignment. I'm sure they have a website, but to make it easier for me to grade, I just want you to use this copy on the off chance that the spans are 3 inches different now on the website. So use this copy that's posted up to Blackboard. So and I don't know, these are called truss joists, so they're TJIs. No, I don't know, somewhere in my early career, my mom must have dropped me on my head when I was a baby. I always call these things TGIs, and I don't know why I do, but they're really technically TJIs. So anyway, these are the wood eye joists, which are very, very common. Other people make them, but the Weyerhaeuser versions are called TJIs. Okay, so we need to learn how to read manufacturer's product literature. So this is the product literature for TJIs. I said J at least. Okay, so I want you, you don't have to read every word, but I want you to become familiar with this, and then I want you to answer the following questions. And we're going to show you an example. This is the 8th depth the TJI joists are available in. So depth is up and down dimension. Okay, so if it's 18 inches up and down, that would be an 18-inch depth. So there's 8 different depths the TJIs are available in. And then they come in different series. And so there's a diagram that shows what's the difference between the series. And then I ask you a question, why the 230 series can support more load than a 210 series if it's the same 9.5-inch depth. So your main use of this in the real world would be to size your floor joists based on their span charts or their span tables. Why would it be important for a designer to get in the ballpark for his floor joist depth? I gave you a hint on one of them. One of them is if I was trying to get an accessible house with a ramp, I need to know how far that's going to be up above the ground so I can do my ramp the right way. What's the other thing that I'm worried about? How far my floors are apart from each other. It's going to affect ceiling heights in a, not really, but as much as your stairs. Okay, so if I'm on my basement and I've got a 9.5-inch deep floor above, I've got the same ceiling in my basement, but my stair has to go up that extra 9.5 inches to get to my first floor. Now imagine it's 24 inches deep. I've got to add more treads and risers to my stair to get up there. And a lot of students forget about this when they design their house, either a habitat or a capstone. And they're like, oh yeah, I'm going to do a 9.5-inch deep floor. And then they realize that their spans are such and they don't want columns in their basement. And we need to have like an 18 or a 24-inch deep floor. And now their stair won't work in their design because they can't get a stair in there. So that's why, as a designer, even if we're not technically designing the structure, we need to get ourselves in the ballpark. So I'm giving you half of the points on this assignment for reading the chart. So I'm going to show you how to do the first one here. So using the floor span tables for a simple span floor, what are the maximum allowable spans for the following I choice? So pay attention because this is 5 points on your assignment. So let's see if I can minimize this somehow. Do this, let's try it. Can I get rid of that? So we want to find, based on, I'm going to show you my example here, based on an 18-inch depth TGI, that's a 360 series. Remember deflection, we're going to go with L over 480 deflection. We have a 40-pound live load and a 10-pound dead load at 16 inches on center for a joist spacing. What's the maximum span? So I did one for you as an example. I'm going to show you how I did that. So let's look at what we got. I'm just going to keep going on until I find the floor span tables. So these are design properties not needed for here. What does this say? Floor span tables. Okay, so now my eyes light up. This is where I need to do it. So I need to find my 18-inch depth. And you can see if I zoom in here, this only goes up to 16 inches. So I cannot find the answer on this chart. So what am I going to do? I'm going to keep scrolling because I know people would ask me a question that I can't find the answer to. And the goofy way they did this chart, this book here, they've got a section with the exact same information for 18 to 24 inch deep joists. Okay, so we're going to go till we find the blue table. So if I'm asking you anything between 18 and 24, you got to come down and find the blue table. So now that we're on the blue table, this is floor span tables. It's not floor load tables. So we're just going to focus in on that. So I'm just going to zoom in on that so I don't confuse ourselves anymore. Okay, so now let's work our way across. The first thing is the depth is 18 inches. So I'm going to be at an 18-inch depth here or an 18-inch depth here. Now, which chart do I use? I got to look at what I've got for deflection. So on my example, I want an L over 480 deflection. So that means that I'm going to totally ignore the L over 360 to answer this question. I'm going to be only in this table here. So now I know I'm in the 18-inch. I've got L over 480. Then I need to know the TGI series. So I'm saying it's a 360 series. So that means I'm going to be in this top row of the top chart, because that's the 360 18-inch L over 480. Then I need to know my loading. So I'm telling you 40 live load and 10 dead load. So that means that I'm going to be in this area here because this is 40 and 25. So I know I've narrowed it down to these top three numbers. And then the last thing I need to know is the spacing on center. So I'm at 16 on center. So I'm at 28 feet, 8 inches. And that's the answer there. Now, it seems really logical, right? When you think about it and you do it this way, but I can guarantee you every year students get at least one wrong in the class, or sometimes one person will get everyone wrong in the class, okay? They'll get everyone wrong, they'll get all 5 of them wrong. So don't just think that because it's logical and it's simple, you can just breeze through it without paying attention. You gotta be, okay, which chart am I on? Okay, which series am I on? Okay, which spacing I'm on? You gotta be very undistracted and being methodical, but you should be able to get all 5 of those then. Then the next question is, what page of the guide deals with more detail on the exterior deck attachment? I've got a question about drilling a hole. Is it true or false? And in what page of the guide did you find the answer? So as you scroll through, you're going to see there's one that talks about drilling holes in the joist. And then there's this page or a section that talks about which joist hanger, those are those metal hangers. What would be the right one for a Simpson hanger for this certain size of depth, and what is its load capacity? So it's not super hard, but take your time and be logical, especially when you do those floor span tables. So that's one assignment. Let me show you the second assignment. Second assignment relates to trusses. So let's find that one. So in this one, I actually took the span chart for a truss and I didn't make you look through the whole thing. I just cut it and pasted it into a Word document. So based on my PowerPoint, all these answers are directly out of my PowerPoint. But now we've got the same thing going on where I'm asking you to pick a floor truss depth for an actual condition. And it's a similar concept, but again, by making it so easy for you, it really requires you to do everything right. Otherwise, you're going to end up with a floor truss that's not the right size or a floor joist that's not the right size. So I'm going to show you my examples. We have a 4x2, which is basically a way of saying 2x4, except it's laying on its side, so they call it a 4x2. And then we have a 3x2, which is basically a 2x3 laying on its side, where it's 2.5 inches instead of 3.5 inches. Okay, so the first thing we need to know is which chart are we going to look at? For the lumber size, I've got 3x2, so that means I'm always going to be in this right side chart for my example. Then I need to know my center to center spacing. So in my case, it's 24 inches on center. So that means I'm going to be in this bottom 2 rows of the right-hand yellow chart. Then I need to know my deflection limit. So in this case, I'm at L over 480 deflection. So that means I'm L over 480 at the bottom here. I'm going to be in this bottom row on the right-hand chart. And then the actual span I'm doing is 18 feet. And so I'm asking you to please enter the truss with the least depth that can be used in the following scenario. So if I'm spanning 18 feet, can I use a 12-inch deep truss? No, I can't. Can I use a 16.7? No, I can't. This is the closest to 18, but I can't use that because it's less. I've got to be, if I need to span 18, I can't give me one that's only rated to span 17 foot 10 because I'm going to be overstressing it. So I've got to go to the next one above the number I'm interested in, which is I want to go 18. So I'm using the one that's rated for 19 foot 1. And then I read up, and that's an 18-inch depth truss. Okay, so again, I've got 1, 2, 3, 4. Again, half your assignment is being able to read this chart right. Okay. Any questions on these assignments? I think you're going to be able to get them done before end of class today. If not, they're due start a class on Tuesday. Okay, that's all I got. Thank you.